what we're going to learn in this class is we're going to learn about the different mechanical properties of materials and how we test for them. And what do they mean? Like, what do strength, compressive strength, or tensile strength means? What does hardness mean? What does impact strength or fatigue, creep means, right? And also we will learn about the failure of metallic materials. Actually, in this class we will learn about the mechanical failure of metallic material, because we've learned about the chemical failure in the videos that you've watched and did the quiz before, right? And everyone did quite well in the quiz, so I assume you've all understood the video lecture. All right, so for this class, we will start with tension and compression. So this is the sort of machinery we use to test for tensile strength and compressive strengths of a material. Right. So basically, it is called a universal testing machine. Okay. So basically, you will have some sort of a jig or fixture to fix your specimen in there. Right. So you have your specimen. You have a jig or fixture to clamp on the specimen, and then you start to move the crosshair. Okay. In this machine, the crosshair is moving up. Right? In this machine, the crosshair is moving down, but it has the same principle. Okay. So basically, you are trying to move the crosshair, right? So you are pulling on your specimen. Okay. At the same time, you are using a load cell to measure the load or the force the specimen is experiencing. Right? So you are using the load cell to measure the force. At the same time, you are using an extensometer to measure the extension. Okay. So while you are pulling on your specimen, so while you are pulling on your sample, you are measuring two things. Okay. You are measuring the force using the load cell, and you're using the extensometer to measure the extension of the specimen. So from these two parameters, from the force and the extension, you can get the stress, which is force divided by the cross-section area, and you can get the strain, which is the change in length or the extension divided by the original length. Okay, so why we don't talk about force or the change in length, because we have to normalize it so that we can compare different type of material together, and we can compare different shapes and sizes of material. Right? So that's why we are using force divided by cross-section area. So it doesn't matter what material we are using, it doesn't matter what size of material we are using, as long as we normalize the force by the cross-section area, we are talking about the same magnitude of force, right? So we are talking about stress. Okay. And the same is true about strain. We are talking about the same magnitude of displacement. You can think of strain as the material's response to external loading. Right? So when you are pulling something, the material will respond by getting longer. Right? So you can think of the strain as the extension of the material. Okay. And okay, as you're pulling the specimen, right? You're pulling the specimen. It is getting longer. You can see before loading, and initially after loading, you start to get uniform elongation. Okay, so if you are plotting a graph of stress on the y-axis and strain on the x-axis, so basically you are plotting this value here, stress, which is force divided by cross-section area on the y-axis, and you're plotting strain on the x-axis, you'll get this graph, right? So initially, you will get elastic property of the material. You get up until this point, and then you will get a plastic property of the material. I will explain more about the elastic property and plastic property. But as you can see, as you apply the load, the specimen is getting longer. Okay. Initially, you will get what is called a uniform elongation. That means the length is getting longer and the cross-section area is getting thinner, but the cross-section area is getting equally thin along the length of the specimen. Right? This is called uniform elongation. Up until this point M here. Okay. At point M, what happens? What happens at point M here, you start to get necking. Okay. Necking is a local deformation. You can see a neck here forming. Right? At point M, you start to get necking. And because of necking, you don't get uniform elongation anymore. And then you start to get like the growing of the neck and eventually the failure or the breaking of the specimen. Okay. Okay, so this is a typical stress strain curve. Okay. To be specific, it is a typical engineering strain curve. Not true stress, not true strain, because we don't really use true stress or true strain because it is difficult to measure. Okay, so you have to understand first of all, true stress and true strain is the actual force. Well, we're talking about true stress first. True stress is the actual force at that time divided by the cross-section area at that time, right? But as you can see, the cross-section area changes all the time as you're pulling it. The cross-section area is getting smaller, the specimen is getting thinner, right? So you're not sure what is the cross-section area at a given time. But we know the cross-section area A for a standard sample, right? We know for standard sample, like in this picture here, we know that the cross-section area is A0, right? So if we are dividing the force at a given time, which we can find from the load cell, okay? The load or the force at a given time is measured by the load cell. And we divide the force by the cross-section area of the specimen, which is A0. Here we get engineering stress. For engineering strain as well, we get the extension divided by the original length. We get the engineering strain. And we plot this engineering stress strain curve. Okay. Okay. Okay, so are you still with me so far? Okay, so initially, like I mentioned earlier, you can see that it has this elastic behavior, right? Elastic in this case means reversible. That means when you're applying the load, the specimen will get longer, right? When you're applying the load, the specimen will get longer by increasing the strain, right? But when you're removing the load, the specimen will change back to the original shape and size, just like when you're pulling on an elastic band. Right? When you're applying the load, the elastic band will stretch, but when you remove the load, the elastic band will shrink to the original size. Right? This is called elastic behavior. The reason for that, okay, let's skip to the next slide. let's skip to the next two slides, I think. Okay, so this is the elastic behavior. You can see that when you are, okay, to start off, we have a piece of steel, right? Say steel, a piece of material, any material, say a piece of steel, right? We fix the top end of it to the ceiling, and we start pulling on this side. We start pulling this piece of steel. Okay, so initially, before applying any stress, you can see that it has the original length, this length here. Okay? And if you zoom in, you will see the atoms arrange themselves like this in this piece of steel. Right? So when you are pulling on it, you apply your force F, you're pulling on it, this piece of steel is getting longer. Okay? Initially, it is getting longer by the extension delta, and it is getting longer because of the stretching of the bonds between the atoms. You can see the planes of atoms, right? This plane of atoms is this plane here. This plane of atom is this plane here, right? You can see that the distance between each of these planes increases. This is called bond stretching because you are stretching the length of the bond between the atoms. But you're not breaking the bonds, right? You're not breaking the bonds yet because you're applying a force that is not high enough to break the bond. Okay? So when you remove this force F, what happens is that the plane of atoms will return to the initial points. Okay? They return to this position. So in the end, you would get the same piece of steel with the same length as originally. Right? This is called the elastic behavior. Okay? Because elastic in this case means reversible. You can have linear elastic or non-linear elastic. You might be more familiar with linear elastic, but if you've heard of Young's modulus, Young modulus or elastic modulus, that's the elastic, linear elastic property of it. Okay, so that elastic property can be applied up to elastic limits, and then you start to get plastic deformation. Okay, so that means even if you remove the force, your specimen, the sample, will stay deformed. You cannot change it back to the original shape or size anymore, right? It will stay deformed. Okay. And in this graph, the property that is interesting is the elastic limit here, right? Or we would call that a yield strength of a material. A yield strength is the stress that we need if we want to deform it into the certain shape that we want. For example, if you have a sheet metal, like or you have a sheet metal, and if you want to form it into, say, a car door, you have to apply stress higher than the yield strength or the elastic limit of the material, so that piece of steel, that sheet metal, will stay as a car door. It doesn't like spring back to that original sheet metal, right? Another property that you can see in this graph is at point M here, right? This is the tensile strength of TES, right? Tensile strength of the material. That means it is the highest stress that material can withstand, right? That is the highest or maximum stress that material can withstand. And the point F here is the fracture strength. So the stress at which your specimen breaks. Okay. So if we consider the elastic portion first, okay, like I just mentioned, you might be familiar with Young's modulus. Okay. We use a symbol E here for Young's modulus, or more generally known as modulus of elasticity. And if you look at the graph of stress and strain, right, you will see that the slope of the graph is actually the Young's modulus, or the modulus of elasticity, right? So if you rearrange this equation here, you get E equals stress divided by strain, which is the slope of the graph. But remember, it is an elastic property, therefore it only applies to this range of the material, right? The slope of the graph, or the Young's modulus, only applies to this range. Um, that means it doesn't apply to when it already deformed, because the slope changes. And what does Young's modulus tells you? What does elastic modulus, or modulus of elasticity, or the slope of the graph tell you? Okay, so if you look at the modulus of elasticity for different material here, you can see that for aluminum, the elastic modulus is about 69 gigapascal. For brass, it's about 97, copper 110, magnesium 45, steel 207, titanium 107, and tungsten 407. What does that tell you? It tells you that some material are stiffer than others, right? So the higher the elastic modulus tells you that that material is stiffer. That means it is more difficult to deform elastically, right? For example, steel is much stiffer than aluminum, right? So aluminum can be easily bent, easily like deformed elastically. It will spring back, right? If you don't apply enough stress, it will spring back to the original shape. But aluminum is it's more easily deformed than say steel or nickel or titanium, right? These materials are more difficult to deform, elastic. And when the elastic modulus is important, for example, when you are designing something like aircraft wings, if you notice, before takeoff, the wing of the aircraft hangs quite low, right? But during flight, the wings just like lift up a little bit because of the lift acting on the wings. But we don't want the lifting or the bending of the wings to be permanent. So we have to choose a material with high enough elastic modulus so that the wings doesn't bend too much during flight, or you will lose all the aerodynamics that the wings were designed for. Right? So the wings will just lift up a little bit, and then when the plane lands, the wing will go down to the original position again. Okay? So you have to choose a material with high enough elastic modulus so that the wing doesn't like go up so high, so that you lose aerodynamics and you lose lift, and the plane cannot fly anymore. Right? But at the same time, you cannot choose a material with too high elastic modulus, because usually material with too high elastic modulus are really brittle. Okay, so it will break easily, right? So it might not bend so much, but it bends just a little bit, and then it breaks straight away, right? So we don't want that either. So you have to choose and pick a material with high enough elastic modulus so that it doesn't bend too much, but not the elastic modulus mustn't be too high that it becomes too brittle. Okay. So in that brief 20 minutes, we've learned about yield strength of a material, right? We've learned about tensile strength of material. We've learned about elastic modulus of material. We've learned about elastic property of material, right? So that's quite a lot of things that we cover in the past 20 minutes, right? So that's something that you have to be aware of, right? Okay, so the elastic property, okay, I've covered that. Okay, so the next thing that we're going to go into a little bit more detail is yield strength or yield point of materials. Okay, some materials have a clearly defined yield points, like the one on the right hand side here for low carbon steel, right? So you have an upper yield point and a lower yield point, and we take the lower yield point as our yield strength of the material. Okay, so that's quite simple. And we have like a list of different, we have a list of yield strength of different materials. But sometimes the stress strain curve is not clearly defined. So we have to define a point where we use as the yield strength of a material. Okay. Okay. So we use something which is called 0.2% strain criteria or 0.002 strain, right? So we add strain of 0.002 or 0.002, and then we draw a line parallel to the stress strain curve, and where that line intersects with the stress strain curve, you would get your yield strength. Okay? Because yield strength of a material is defined as the stress at which you get a noticeable permanent deformation of a material, right? But there was a debate: what is noticeable? Like 150 years, 200 years ago, there was a debate like how much strain is noticeable. So it depends on the resolution of the measuring tools at that time, and they came to a conclusion that a strain of 0.002 is quite noticeable, quite measurable with the tools at that time. Like nowadays, we can measure in more detail than that, but we still use this as a criteria, right? So we measure a permanent strain of 0.002. We draw a line parallel to the stress strain curve, and then when it intercepts the stress strain curve, we get the yield strength of the material. Okay, yield strength is the stress at which we need to permanently deform a piece of material. Okay, so we want to shape it into the shape that we want, then we have to apply a stress higher than the yield strength. Okay, and the yield strength is the minimum stress that is required to permanently deform a piece of material. Okay. Permanent deformation, in other words, is called plastic deformation. Okay. So if you recall, elastic deformation when you get bond stretching, right? And when you remove the force, the planes of atoms go back to the same position. That's elastic or reversible. But if you apply more stress or more force to it, you start to get bond stretching initially, and then you start to get plane shearing. You can see that the plane of atoms are not the same anymore. This atom here used to be here, right? This atom here used to be here, right? So you can see that the plane of atoms sort of like slides down, right? Or this is called plane shearing. Okay, so while you are applying the stress, the increase in length of the sample is from delta elastic, or the from bond stretching, and also delta plastic from plane shearing. And when you remove the stress, as we can see from elastic deformation, the bond stretching will disappear, and you'll be left with plane shearing, right? So you have a permanent strain or plastic strain. Okay, so basically, if you want to form a piece of metal or fit a piece of material into a new shape, you have to apply a stress higher than the yield strength, so that you would get plane shearing, so that you would get plastic or permanent deformation. Okay. Okay, let's have a look at this stress strain curve. Right? So, if you're applying a stress up to point D here, okay, up to point D here, as you're applying the stress, or you're still pulling on the specimen, right? As you're applying the stress, the overall strain, or the total strain is the elastic strain plus the plastic strain, right? So basically, you have the total strain of 1 and 2 here. So the total strain is this point here, right? You have the plastic strain and elastic strain, right? Elastic strain, plastic strain, right? So the total strain while you are still applying the force is this much. But when you are removing the load or removing the force or unloading, the specimen will try to shrink back to the original shape because of the bond stretching. You can see that the slope of this line here and the slope of this line here is roughly the same. It is not roughly the same because of the same behavior, right? This line, the slope of this line is caused by the bond stretching, right? I'm sorry, bond stretching, right? Initially, you have bond stretching. So when you're removing the stress or unloading, right? The stretch bonds or the plane of atoms that are further apart, they will try to shrink back. So basically, on this line, you are pulling the plane apart, and on this line, the plane just shrink back to the original shape. So it is the same behavior, just going forward and going backward. So that's why you have the same slope, right? For this line and this line. Okay? But remember, this is after you unload or you're not applying a load, right? But because of the plane shearing, okay, as you're applying stress, like more and more stress, larger and larger stress, you get plane shearing. So even though you're removing the stress, you will get rid of the elastic strain, which is number 2 here. But you're left with permanent strain from plane shearing. Okay, so you get this like permanent elongation. Okay. Okay, so what you should know now is what is yield strength of a material, right? What is the tensile strength or the ultimate tensile strength, like the peak of the graph, right? You should know about the elastic modulus or Young's modulus. Um, okay, and you should, well, I haven't covered ductility, resilience, and toughness yet, but I'll do that soon. Okay. Ah, okay. Actually, I think Ajahn Visada might have covered this. Alright, okay, okay, next property that we're going to look at is the hardness, right? Okay, what is hardness? What is hardness? Okay, so um, it's a good thing that we're taking this class in English because in Thai, right? Hardness and strength sounds really similar, right? ความแข็ง and ความแข็งแรง So a lot of people get confused by the concept of hardness and strength. But actually, they are quite different, right? So when we're talking about strength, like yield strength or tensile strength, we're talking about the whole piece of material requiring or withstanding a load, like the whole piece withstanding like a load before deforming, right? So basically, strength is the ability of the material to withstand a certain amount of load before deform elastically or plastically, right? But hardness is actually um, hardness is actually um, the ability of a surface to withstand plastic deformation. Okay, so something that is really hard, that means the surface can withstand deformation. So the surface can prevent indentation or denting of the surface if the surface is hard. Um, okay, so when you buy a new phone, what would you do actually? Like, what is the first thing that you normally do when you buy a new phone? You would put on a protective film, right? You put on a screen protector, right? But why? Why would you put on a screen protector? Just okay, you might think that you don't want to break the screen, right? And you would choose a screen protector that is really hard, has really high hardness, something like that. But actually, high hardness doesn't actually help if you drop your phone, right? If you drop your phone, the screen protector with high hardness doesn't help you at all, okay? Because the hardness is the property of material that withstand surface deformation. That means if you have keys or coins in your purse or in your wallet, in your pocket, those keys and those coins will not scratch the surface of the screen. Okay? They won't be scratched, but if you drop a phone, the screen protector won't do anything. It won't protect the screen from like cracking. Okay, so hardness is an important property, and the hardness tests are performed more frequently than any other mechanical properties for several reasons. The first reason is that the hardness is quite simple to perform and they are inexpensive. Right? You don't need any special sample preparation, and the machine that you use to test for hardness is quite cheap, like a few $100,000, like relatively cheap. And the hardness testing is non-destructive. Non-destructive, that means you don't destroy the specimen. You can use that specimen again. Okay? The specimen is neither fractured nor excessively deformed. You only have a small indentation as the deformation, so you can reuse that specimen. Um, and the most important things why the hardness test is performed most frequently. The most important thing is that other mechanical properties can be estimated from the hardness data, such as tensile strength. Okay, so as you can see, when you are doing the tensile testing machine, right? When you are doing the tensile test, you need a specimen of a certain size, like quite big specimen. You need some sort of like machine which is quite expensive. You need extensometer, you need load cell to do the tensile test. But for hardness tests, it's much simpler. The machine is not as expensive, and you can get an estimate of the tensile strength from the hardness test. Okay. There are many different types of hardness tests. We'll look at these different hardness tests like one by one, but all of them share the same sort of like principle. Okay, so basically, you're trying to indent or put a scratch on the surface and measure how far or how deep that indentation will go on the surface, and we can compare different materials looking at different like indentation, right? Okay, so this slide is sort of a summary of all the hardness tests that we can do, like Grinnell test, Vickers, New, Rockwell, etc. But I'll go into more detail, like each one of them first, and then we'll come back to the summary. All right. So, for example, Grinnell hardness test. Okay. The Grinnell hardness test is quite an old technique that was invented a long time ago in Sweden by Dr. August Grinnell. Basically, you take a ball bearing, right? You take a ball bearing with a known diameter. You have a ball bearing of a known diameter. You harden the ball bearing, and you push the ball bearing onto the surface. Usually, the diameter of the ball bearing, the steel ball bearing, is about 10 millimeters. Right? So basically, you have this bigger B diameter of 10 millimeter. You you use a certain force, that range from 500 to 3,000 kilograms, right? To push that ball bearing, that small ball bearing, onto the surface. Once you put the ball bearing on the surface, you remove the ball bearing, and you will see this indentation on the surface, right? You will see a hole caused by the ball bearing, right? You see a hole caused by the ball bearing. You measure the diameter of this hole here. You measure the diameter of this hole here. You get this d, small diameter, and you put it in this formula here. You will get the Grignard hardness, right? So you know the force, you know the big D, which is the diameter of the ball bearing. You know the small d, you can measure the indentation. So you can get the hardness in the Grignard scale. Right? So you can see that for a soft material, right? For a soft material, the ball bearing will go in deeper. So the ball bearing will go in deeper. That means this D, this small d here, this small d diameter of the indentation will be bigger, will be closer to the big diameter there, right? For a hard material, the indentation will be quite small. It would have small d, right? So from that, right, for hard material, you would get a higher number because you have small d here, right? But for soft material, these two values are getting closer and closer, right? So you will get smaller and smaller number for the hardness, right? So the higher the hardness number, the harder the surface, right? So for Grignard testing of hardness, you're using a steel ball bearing or tungsten carbide ball bearing of known diameter, usually 10 millimeter. You're using a certain force that you know. Push that ball bearing onto the surface. You're measuring the indentation, which is this small d here, which is from this picture here, right? And then you can get the hardness, and you can compare hardness of different material. Okay. And for really hard material, usually we use other technique, like apart from Grignard, we use something like viscous or noob hardness. Okay. Noob and viscous are very similar in a way that they have a pyramid shape indenter. Right, so this is viscous, you have a pyramid shape indenter. Noob, you also have a pyramid shape indenter that is made from diamond, right? Viscous and noob are similar, that they have pyramid shaped diamond indenter. So it's the testing head itself is really hard. Okay, and you push this indenter on the surface, and you would get this indentation. Okay, you get the pyramid shaped indentation. The lower one is for viscous, right? Because you have equilateral pyramid here, so you get this shaped pyramid here for viscous, and you get this shaped pyramid for noob, right? Both noob and viscous are very good with hard material. Like when you are testing for, say, enamel coating of a tooth, of a full tooth or whatever, we can use these two techniques to test for the hardness of the coating, whether it is good enough or not. Okay, so basically, you're measuring the indentation, right? So for viscous, you're measuring how big is the indentation on the surface. For new, you're measuring how deep the indentation goes. And from that, you would get viscous hardness and noob hardness, right? And you can compare the hardness of different material by that measure. The next is Rockwell hardness. The Rockwell hardness is the most simple and easy to use technique. The machine just does everything for you basically. It is the most commonly used method. It can be used with a wide range of material, but like I mentioned earlier, like really hard material, you would need some specific technique like nuke or Vickers. But Rockwell is easiest to perform, and it gives you a number straight away. You don't have to measure the indentation, right? So if you look at the Rockwell hardness, you don't have any formula to calculate the hardness, right? So the machine will give you the value straight away. Okay. Rockwell hardness have two main scales, right? The Rockwell hardness have one of the main scale is the B scale, and the other main scale is the C scale. Okay, so the B scale Rockwell hardness will use a ball. Okay, a ball indenter, whereas the C scale of the Rockwell hardness will use a cone indenter. Right, that's where the B and C scale come from. B for ball and C for cone. Okay, so basically you either have a cone shaped indenter, which is made from diamond, and or you have like tungsten carbide or hardened steel ball as the indenter for Rockwell hardness, right? So basically, what you would do is you prepare your sample, you put it under the testing head, you apply a minor load so that the testing head will just sort of dig in a little bit on the surface, and then you apply the main load, right? So, and it will go through your specimen, and then you release the main load, and you measure the depth that the indenter traveled when you apply the main load, and the depth of the indenter gives you the hardness value in either HRC, which is the hardness Rockwell scale C, or HRB, which is hardness Rockwell scale B, right? So the main point to remember here is B is short for ball, right? And C is short for cone, right? The B scale is usually used for softer material like aluminum, brass, softer steel, and because it uses steel balls as indenter, so the steel ball is not really hard itself. But if you want to test really hard material, you would use hardness Rockwell scale C, which is the diamond cone, right? Hardness Rockwell scale C, you're using a cone-shaped indenter, okay? That is made from diamond, right? So you have a diamond cone, and that is used for harder material. Okay, so that's hardness. What does hardness tells you? What does the value of the hardness testing tells you? It gives you the sense of wear resistance of the material. The material with higher hardness will be worn down much more difficult, right? So for example, if you're choosing a material for I don't know, for a false tooth, for example, you know that like acrylic, traditional acrylic false tooth is relatively quite soft compared to porcelain or glass ceramic uh, tooth, right? Because glass ceramic has higher hardness, it will it will be worn out much slower than the acrylic false tooth, right? But at the same time, if your fortune or your crown is too hard, what would happen? It will wear down the natural tooth around it, right? So you have to choose carefully when you are choosing material or when you're producing material, like for a crown or for a fortune. You don't want to wear down the natural enamel of um, the tooth that is like biting on that fortune. Right? So that's one of the problem with um, glass ceramic or porcelain fall tooth or crown because it is too hard. It will wear on the natural tooth uh, that is remaining. Right? Okay, so hardness tells you about wear resistance, right, or abrasion resistance. Okay, the harder the material, it will be worn out or it will be worn down much more difficult. Right? Also, for something like knives and sword, you would need something that is really hard to keep that cutting edge. You might have heard like some like top surgeon they would use uh, um, a scalpel that is made from obsidian instead of like normal steel, right? Because obsidian is some sort of natural glassy type rock, and it is really hard, and it can keep the sharpness really well, right? So this it wouldn't cause like so much of a scar compared to normal steel scalpel. Okay, so next, next we will look at the impact property. Impact property of a material, okay, can be tested using a simple impact testing machine. Okay, so basically you have this sort of a big hammer here. It quite weighs quite a lot for um, polymers and ceramics. This machine can be tabletop, right? It can be about like 30 centimeters to 50 centimeters high, right? So it's like big. It's not that big of a machine. But for metals, this machine can be about 2 meter high. This hammer can be about 100 of kilograms, right? But for ceramics and for polymers, for the smaller machine, the hammer would weigh about 500 grams, not much more. Okay, so basically, you take the specimen, you put the specimen here, right? You can either do the choppy test, right, by putting the specimen horizontally, or you do the eyesore test by putting the specimen vertically. Right? So the specimen is pre-notched, right? So you have this like standard size specimen, and then you pre-notch it, either a V notch or U notch, right? Depending on the standard you are following. So you have a pre-notched specimen, you put it in, say, a choppy testing machine, you put the specimen in horizontally. Next, what you would do is you lift up this hammer, right? So when you lift up this hammer, you know the mass of this hammer, right? Say, for example, if we're testing uh, polymer sample or ceramic sample, that hammer would weigh about 500 grams, right? So it's not a big weight, so that's just 500 grams, right? So you lift it up, you know the mass, you know the height, right? You have this relative or reference point here. So you have the height, you have the mass, so you know the potential energy of that hammer, right? So basically, it's just mgh, right? Mg mass times gravity times the h, the height here, right? So you know the potential energy on that hammer. Once you let that hammer go, all that potential energy will transform into kinetic energy and it's travel down and hits your specimen. Okay? After the hammer hits the specimen, the hammer will travel up. How far the hammer travel up depends on how much the specimen absorbs the energy. Okay? So for example, if your specimen absorbs a lot of energy, the hammer, after traveling so far, the specimen, it will go up by this amount, h prime, right? So not so much. But if the specimen doesn't absorb a lot of energy, after the hammer hitting the specimen, the hammer will travel up further, right? Because initially it has this mgh amount of energy, right? Some energy will be absorbed by the specimen, and the rest will be transformed from kinetic energy to potential energy. Okay? So if we can measure the final height of the hammer, like the h prime here, we will know that we will know how much the specimen absorbs the energy, right? By using mgh minus mgh prime. Okay? So we will know how much the specimen absorbs the energy. If the specimen absorbs a lot of energy, the h prime will be quite low. Okay? If the specimen doesn't absorb a lot of energy, the energy h prime will be quite high. Right? So imagine if you don't put the specimen here. So basically, if you let the hammer go, the hammer will transform the potential energy and kinetic energy and go up to h level height on this side, right? Okay? Because it doesn't lose any energy, but because we have a specimen like obstructing the travel of the hammer will hit the specimen will absorb the energy, and the hammer will travel with the remaining energy. Okay? So it is difficult to measure h prime, but we can measure the angle. I use this pointer, and if we know the length of the arm of the hammer, we can find the h prime quite easily. Okay, so so what does that mean? What does the specimen absorbing energy? What does that mean? If the specimen absorbs a lot of energy and the hammer goes up, and the hammer goes up like quite low, and the specimen absorbs little energy and the hammer goes up quite high. What does that mean? Okay. It means that we have different types of material. Okay. If the hammer, after hitting the specimen, goes up to a height, like quite low height of H prime, that means that material is a high toughness material. Okay? it absorbs a lot of energy before it breaks. Okay. Whereas if the hammer, after hitting the specimen, goes up quite high, that means that material has very low toughness. Okay. So, in other words, toughness is the amount of energy required to break a certain volume of material. Okay. You can think of toughness as the energy you need to break it down. Like when talking about toughness, I want you to think about a piece of steak, right? If the steak is tough, what do you have to do? You have to chew it for a long time, right? It requires a lot of energy to break down the fibers, right? So that is a tough piece of steak. But for uh, a piece of steak that is not so tough, you chew it for a little bit and you can swallow it, right? The same with material. Right? A material with high toughness requires a lot of energy to break it down. Material with low toughness requires little energy to break it down. Um, okay. The energy is used to produce new surface. Okay, so each material has like surface energy, and the total amount of surface energy depends on the surface area. You can see that the area which is called dimple, this area here, right? And this area here, right? Looks something like this. Yeah, looks like you have a lot of like holes or pock marks on the surface, right? And when the surface looks like this, you have a lot of effective surface area because it's not flat. You have like a lot of valleys, and you have a lot of peaks, right? So you have a lot of effective surface area. That means if you look at the fracture surface and you see a lot of dimples, like in this picture here, right? Compared to well, cleavage, you have low amount of cleavage, low, relatively small area of cleavage, and high area of dimples. This is a typical tough material, right? For low toughness material, you would have high amount of cleavage, like this relatively flat fracture surface compared to like, right? This is the microscopic scale, right? When you look at the surface. But if you look at the specimen like on a more macroscopic scale, you can see that for a high toughness steel compared to low toughness steel, you can see that the surface and the specimen is sort of like distorted a little bit, right? It's not flat compared to low toughness. You see the fracture surface is quite flat, right? Low toughness is quite flat because it doesn't need a lot of energy to produce new surface. So the surface is quite flat. And you can see that it takes about 10 joules to produce this, like, well, I'm sorry, the specimen only absorbs about 10 joules before breaking. And you can see that the amount of the brittle fracture is about 55%. The brittle fracture refers to the cleavage. Right? So if you have a lot of cleavage, that means that material has a lot of brittle fracture. For steel with high toughness, you can see that it absorbs 28 joules before it breaks, and there's only 1% area of cleavage. Okay. And you can see the specimen is sort of like rougher. It's not like the fracture surface is not flat, and the surface itself, if you look at the surface itself, is quite rough. You have a lot of dimples compared to this picture here, which is like flat. Okay, and when we do the toughness testing, when we do this impact testing to our specimen at a range of temperature, and we do it to a whole lot of materials, we would get a graph that looks something like this. Okay? We would get a graph that looks something like this, and we can categorize materials into 3 groups. Okay. When we plot a graph of the toughness or the impact energy and the temperature that we are doing the tests. Okay. So basically we do the same thing. We do the impact testing at low temperature, like minus 20 degrees Celsius, minus 10, 0 to 10, 20, 30, 40, 50, like for a whole range of temperature for one material. And then we do the same with another material. We do the same with another material. Right? And then we plot a graph of temperature and impact energy, or the energy absorbed by the specimen. We can categorize materials into 3 groups. Like the first one is this one here, like the high strength material. You can see that from the graph, you can see that the impact energy is low, right? For all range of temperature. What does that mean? That means high strength materials are usually quite brittle at all temperature range, right? So it doesn't matter what the temperature is, this sort of material, this high strength materials remains quite brittle. Okay, so it breaks really easily. For example, like glass, like ceramics, right? Some metals are quite brittle as well. Right? So high strength materials are usually quite brittle, so it absorbs just a little bit of energy. It doesn't matter at which temperature, it remains brittle at all temperature. Okay, that's one class of material. Another class of material is the low strength or FCC and SCP metals, like lower strength metal, but still quite strong, right? And metal with FCC microstructure and SCP microstructure. You can see that it absorbs a lot of energy, right? The impact energy is quite high at all temperature, at all range of temperature, right? From low temperature to high temperature. And it observes the same trend as the brittle material, that when you increase the temperature, the impact energy absorbed will increase a little bit, right? For high strength material as well, you can see that the graph like goes up a little bit. And for tough material, the graph also goes up a little bit as you increase the temperature. Right? Okay. So those are 2 types of materials that's not very problematic, because we know what we get, right? We know what we get because we know that high strength material is brittle at any temperature. So when we use it, we know that we have to be careful that it doesn't absorb a lot of energy. In other words, we have to be careful that it doesn't take any impact or it will break. Okay? On the other hand, for tough material, we know that it can take a lot of beating before it breaks at all temperature. Right? So we don't have to be too careful with these 2 types of material. But the third type of material, this blue line here, this is quite dangerous because we have to know exactly what type of temperature we are going to be using this material, right? Because at high temperature, it will behave like a tough material, but at a low temperature, it will behave like a brittle material. Okay? So there was a those some merchant navy ship during the Second World War, oil tanker ship. That before the war, the ships were used to transport gas and oil from the Middle East to the UK. Right, so you go through the Mediterranean Sea, which is quite warm. Right, so they knew that the ship would be operating in the Mediterranean Sea, so they chose a material that is relatively quite cheap, which is a type of steel, right? Low strength steel, because they know that in the Mediterranean Sea, the temperature will be warm enough so that it will perform like a tough material, right? The high temperature will make the material stay quite tough, quite ductile. But during Second World War, the German and the Italian navies like sort of control the Mediterranean Sea. So the British had to go somewhere else to get their oil. So they had to go to Norway to get their oil. They are using the same ship, the ships that were designed to be used in the Mediterranean Sea, the warm Mediterranean Sea, but they were using it in the North Sea, the cold North Sea. So the operating condition changes. So they were operating at a temperature just above zero, right? About 2, 3 degrees Celsius. So that past this transition temperature from um, ductile to brittle. So the ship sort of like broke in half because of the temperature range that they were using it. Um, okay, this is the ship that I was talking about. You can see that the crack is like go through like the mid of the ship, the middle of the ship, right? Because this oil tanker has a brittle crack in the middle because it was designed to be used in the warm Mediterranean Sea, but instead it was used in the cold North Atlantic Sea. All right, so the behavior change from ductile or tough to brittle, and it will break straight away. And this behavior, right, this brittle to ductile transition behavior is influenced by the carbon content of steel, right? So when you change the amount of steels, when you change the amount of carbon in your steel, you will change this behavior. For example, if you have a really low amount of carbon, you can see a sharp transition from ductile or tough to brittle, right? As you increase as you increase the amount of carbon, you can see that it changes from like tough or ductile to a more brittle material, and the transition from brittle okay, so to ductile. The next topic that we're going to look at is called fatigue. All right, fatigue. Um, what is fatigue of a material? Right. If you know French, fatigue or fatigue, you should actually means to get tired, right? So fatigue in terms of material is when material is tired after you using it for a period of time, right? So fatigue of metals, fatigue of material, uh, actually is it comes from Latin roots of fatigare, which means to tire. So the descriptive definition of fatigue is found in the report titled General Principle of Fatigue Testing of Materials. Okay, and it was defined as uh, the fatigue applies to a change in properties which can occur in a metallic material due to the repeated application of stresses or strain, although usually this term applies specifically to those changes which lead to cracking or failure. Okay, so what that means is that when you're using a component for a long time and it had to withstand a cyclic or repeated loading, right? So not a constant loading. You're not applying a constant stress for a long time. Okay, you are applying a repeated stress. You can think of it as the sinusoidal application of stress, right? So, say for example, you start applying stress, positive stress, which is tensile stress, up until the maximum stress, and then decreases the stress until you do not apply, you're not applying any stress at all until you start to apply compressive stress until you get the minimum stress, which is the maximum compressive stress, and change again, right? So basically, the stress is not constant. You keep changing the stresses all the time, from tension to compression. You change the magnitude of the stress as well, right? So when you do that, the material will get tired, right? And it will break. Okay, and as you can see in the picture on the right hand side here, the mean stress doesn't have to be zero. The mean stress or the average stress can be either positive or negative, right? So you have sigma m here, which is the mean stress, and the mean stress can be highly positive, like in this case, yeah, right? So, but the main thing is that the stress is not constant. The stress is fluctuating or changing or dynamic in nature, usually cyclic. Okay, it comes in cycles. You apply stress in cycles, usually cyclic, very dynamic stress, and that will cause cracks or fracture, even though the maximum stress is less than the yield strength of a material. So even though the maximum stress, sigma max here, is less than the yield strength of a material. So you shouldn't even get plastic deformation, right? If you're applying a constant stress, you will not get plastic deformation, but because you're applying a cyclic stress, you can break the specimen. Okay? Fatigue is really, really important because about 80% of mechanical failure is caused by fatigue. Okay? You see that for mechanical failure in materials, 80% are caused by fatigue, right? So we have 60% common fatigue, 8% low cycle fatigue, and 11% heat fatigue or corrosion fatigue or rotary contact fatigue. Right? So about 80% is fatigue. The rest is corrosion, stress corrosion cracking, and static overloading. So you can see that only about 13% is static overloading, or like when you're applying too much stress to a structure. That means as engineers like design components, design structures really, really well. So only 30% exceed the applied stress exceed the strength of the structure. But what engineers didn't figure out was usually the stress that a structure or a component is experiencing usually cyclic in nature. It's not a static stress. It's usually cyclic, right? That leads to fatigue, failure of component, right? So, because when engineers design something, they think of it as apply a constant stress. And when they think about that, the design concept will try to withstand that constant stress, right? That means when the stress is not constant, it can cause failure. Okay? And in many applications, the stress is not constant. Like for example, when you're designing a bridge, you would think that okay, the bridge has to withstand this much loading, how many trucks, how many cars that can go on the bridge, right? How much is the weight the bridge can withstand? Or even when you're designing a building, you're thinking about how much weight this floor can hold without breaking. But that is just constant or static stress. Like the amount of stress that it's not changing, right? But think of a bridge. Usually, the load on the bridge is not constant, right? Because the cars are moving, the trucks are moving, so you can feel the bridge shaking or vibrating. Okay? In a building as well. So if you're walking or you're jumping around, you can feel the floor shaking, the floor moving, right? So that is the cause of fatigue. That constant changing of stress, that cyclic stress, and because um, engineers haven't figured that one out in the design, that's why about 80% of mechanical failure is caused by fatigue. But nowadays, engineers are getting better in predicting fatigue and design for fatigue. So that number, that common fatigue, like is getting lower from 60%. Okay, so how do we test for fatigue? Right? Fatigue testing, we have different levels. We have lab scale tests, we have component tests, we have full scale tests, and then like product tests. Okay, in lab scale testing of fatigue, what we usually do is we are testing different materials to see their fatigue behavior. Okay. Okay, in lab scale tests, we have a specific, like standard specimen, right? So this test specimen is shaped specifically like this. It's sort of like a dog bone or a dumbbell test specimen. But if you look carefully, you can see that the specimen is polished really well, right? So it's polished really, really well. So the surface, the surface is really shiny. Okay, that's a reason for that. I'll talk about it later. Okay, so first of all, we need a standard specimen, and the surface preparation of the standard specimen is also important. So that's why we have to polish it really, really well. And then we do the testing, right? For lab scale tests, we can do testing in two methods. The first one is called rotary, uh, rotating bending or rotary bending machine, right? So basically, you load your specimen horizontally, like in this picture here. You have a load bearing couple like this one, right? Load the specimen. You apply bending, or sometimes you apply a weight on the specimen, right? So basically, you are trying to bend the specimen. Okay, so you are trying to bend this piece here, right? You're trying to bend this specimen here. You're bending it, at the same time as you are rotating it. That's why it's called a rotating bending test. Okay, so because when you're bending it, the top half of the beam or top half of the specimen will experience compressive stress. The bottom half will experience tensile stress. Right? So this is the stress that is experienced by the bottom half of the specimen when you're bending it, right? So this is the compressive stress or the negative stress, right? So the compressive stress is being experienced by the top half of the specimen when you're bending it. But don't forget that you are rotating it at the same time. That means this bottom half will become the top half will become the bottom half, right? So the bottom half now is experiencing tensile stress, but when you are rotating it, the bottom half will become top half, and it will experience compressive stress, right? So the stress, each surface is experiencing changing all the time, from tensile stress to compressive stress, tensile stress, compressive stress. Right? So the stress is not constant; it is repeating, it is cyclic in nature, and that is what causes fatigue failure. Okay? So this is one type of testing that we can do, right? Rotating bending test. Another type of fatigue testing in the lab scale is called tension compression fatigue or push pull, right? So instead of bending the specimen and rotating it, we are pulling and pushing the specimen. Right? So we're loading the specimen in the vertical position, and then we're pulling it, pushing it, pulling it, pushing it, really, really quickly, up to about uh, up to about 20,000 hertz, right? We're doing that really, really quickly. So we're applying stress, measuring the strain, and we are doing that 20,000 times a minute, right? Okay, so for these two techniques, what we do is whether it is rotating bending or push pull, right? We are testing the specimen like for rotating bending. We keep rotating it at a fixed weight, yeah, right? We keep rotating it until the specimen breaks, and then we get a number of cycles that the specimen breaks. Say, for example, we are bending it and we're rotating it up to about 100,000 cycles, and then the specimen break at 100,000 cycles. Or we can do the same with the push pull. We can do that. We can say that the specimen break at after we apply the stress for 100,000 times, for example, right? And we can plot a graph called SN curve. When S is the stress amplitude, which is the y-axis, and N is the number of cycles to failure, which is the x-axis, right? So the stress amplitude is actually the weight, right, or relative to the weight that we are bending the specimen, right? That we are using to bend the specimen, right? The stress amplitude is related to the weight that we use to bend the specimen. Okay, so for one test, we're using that one weight. We're bending the specimen, and we are rotating it until it breaks. It will give us the number of cycles that it breaks, right? It might do 100,000 cycles before it breaks, and we will get just 1 point on this graph here. right? For that one value of the view, that one value of the weight, we get number of cycle to failure, we get that 1 point. We do the same, we change the weight. We change the weight here. We do the same until it breaks, we get another point. We change the weight, we do the same, we get another point, right? Until we get these like line, which is the SN curve, right? Okay, and we can see that the materials can be divided into two types: the one with fatigue limits and one without fatigue limits. Okay? Materials with fatigue limits will look like this. Okay, you can see that the graph stay parallel to the x-axis after a certain amount of like stress amplitude. Right? The number of cycle to failure doesn't change, right? So you can see that about like 300 megapascal. This graph stay constant. Okay, so this is the fatigue limit for this material. But for this material, for the aluminum alloys, you can see that there's no fatigue limit because the graph doesn't stay parallel to the x-axis. Okay, we'll come back to fatigue failure later on in a bit, right? So for this part, I just want you to know the testing methods and how can how can we get the SN curve, right? And I'll come back to this later. Okay, this is the lab scale test. For component test, basically you just take the components, you just put it under the fatigue testing machine, which is a modified tensile tester or a modified universal testing machine, right? So you are doing like keep pushing and pulling until it breaks. Okay, or you can do the full scale test like they do with a car here. They load a car to an actuator, or in fact 4 actuators, and they just sort of like testing the shock absorbing system of the car. And in this case, they're testing um, the plane for pressurized pressurization. Right? So basically, they're putting in water in the plane and see how much of the pressure the plane can withstand. Okay. Okay. For fatigue, you would get really specific fracture surface. Okay. So for fatigue, it is clear that you can see 3 areas on the fracture surface. You get the original crack initiation point, you get fatigue crack growth, and the final overload. Okay, so when you see a fracture surface and the fracture surface show 3 signs or 3 areas, like clearly 3 area of crack, the initiation point, the fatigue, crack growth, and overload, you can confidently say that this component failed because of fatigue. And if you zoom in the fatigue crack propagation or in this area here, you can see fatigue striation. You can see lines where cracks grow. You can see line where crack grows by each individual application of stress, right? So This is like one step that crack can grow, right? Each step that crack grows. Okay. Um, and as I mentioned before, that the surface preparation is important. That's why the surface of the specimen has to be really, really shiny. It has to be highly polished because the usually the crack initiation starts on the surface, and the rougher the surface, the easier it is for crack to initiate. Right. So the fatigue life can be shortened if the surface is rough and you get crack initiation easily. But at the same time, you can improve fatigue life if you improve the surface roughness. You make the surface smoother, you polish the surface, right? If you polish the surface, fatigue life will be higher, right? So if you compare polished surface to ground surface at the same tensile strength, you can see that the polished surface and ground surface, the ground surface will have about 90% of fatigue life compared to the polished surface. Okay, the machine surface will have about like 70% fatigue life of the polished surface. So the smoother the surface, the higher the fatigue life. And also you have to design so that you don't have any stress concentration points. Right? For example, in this case, when you have a bad design like the one on the left hand side here, you can see that you have a right angle here. So you have a sharp angle, so the stress will concentrate on this sharp angle, and the crack will start to grow from this sharp corner here. But if you fillet the corner, you have rounded corner, the stress concentration won't be so high for this corner, so the crack will not start here, right? So in other words, the sharp corners act as stress riser or stress concentrator, and it will be crack initiation points, okay? Because the crack will be high at this point, but if we fillet the corner, the crack won't be so high, and that will be a better design. You will have better fatigue performance. Okay, next property of material is creep. Okay, so if fatigue is uh, the ability of material to be used under repeated load for a long time, creep is the ability of material to be used under constant loading at high pressure, at high temperature for a long time, right? So creep is when you're applying a constant stress, which usually you would expect the specimen to have a constant strain, right? So if you're applying a certain amount of stress, you would expect a certain amount of strain, right? Just proportionality, like Hooke's law or Young's modulus, right? When you are using Young's modulus. So if you're applying a certain amount of stress, you would expect a certain amount of strain. And that strain should be constant if the stress is constant. But if you're using it at high temperature, okay, high temperature in this case is more than 40% of the melting point, or 0.4 TM, right? 0.4 TM or 40% of melting point. If the temperature that you're using the components or using that piece of steel at a temperature above 0.4 TM, you might get creep. Okay. In other words, when you apply a constant stress, if the temperature is above 0.4 TM, the strain will not be constant anymore. Okay, you will get increasing strain even though the stress is constant. Okay, and this strain deformation is called creep. Right? For example, the turbine rotor in the jet engine or steam engine has to withstand constant stress from centrifugal force, right? And because it is operating at high temperature, you start to get creep and you start to get crack because of the deformation. Okay, so during creep, what happens is there are two main mechanisms at play here, right? So because we are applying stress, so we are making plastic deformation, and by making plastic deformation, we increase dislocation density. Okay, so I think you've learned about dislocation with Ajahn Krishna, right? So when you have more dislocation, the dislocation will uh, impede each other, making the dislocation movement more difficult, making your specimen stronger, right? So this is called a hardening mechanism, right? So as you have more plastic deformation, the increased dislocation density will impede the movement of dislocation, making your specimen stronger. But at the same time, high temperature means the dislocation movement is easier, and also the dislocation will annihilate each other. They will move, and then they will meet up with another dislocation and cancel each other out. Okay, and this is a softening mechanism. So you have these two mechanisms happening at the same time. That's why for the stress strain, for the creep curve, right, where you plot the strain, creep strain with time, right? So the x-axis is time, the y-axis is creep strain. Okay, so so if you don't have any creep or the temperature is lower than 0.4 TM, you can see that after initial application of stress, the strain stay constant, right? So this is normal case when you don't have creep, right? When you don't have creep, the strain stay constant with constant stress. But because of the higher temperature, you get this softening mechanism, right? You start to get this shape of the creep curve. You have primary creep, secondary creep, and tertiary creep. Okay, the primary creep is when the hardening is stronger than softening. You can see the strain rate decreasing. Okay, the slope is the strain rate. You see the strain rate equal d epsilon by dt, right? In other words, the slope of this graph here is the strain rate, and you can see that the slope is decreasing, like from really steep slope, it's getting shallower and shallower. Okay, so that means the hardening mechanism is winning out until you get to the secondary stage creep, where the strain rate is constant, right? So you get the constant slope here, where hardening mechanism and softening mechanism is equally strong. And then you start to get necking, and you get tertiary creep when the strain rate increases really quickly until rupture. Okay, and as you increase the temperature or increase the stress, the applied stress, you can see that the creep curve shifts from the green line to the blue line to the red line. Okay, that means the creep will be faster. The creep rate will be faster, and also the fracture will happen faster. You can see that when T3 is more than T2, it's more than T1, right? The graph will shift from this T1, T2, T3, right? So the creep curve will get shorter, it will get steeper. That means the creep rate is faster and also the creep life is shorter. Okay, so at high temperature, you have increase in vacancy. The dislocation will climb to another plane. Dislocation movement and plastic deformation movement will cancel each other out, etc. Right? So you get this annihilation of dislocation at high temperature. Okay, so next we look at standards. So for mechanical properties, there are different standards that we can use, like ASTM, ISO, JIS, DIN. Right? ASTM is the American Society for Testing Materials. So this is the American standard. ISO is the international standard. JIS is the Japanese industrial standard, and DIN is the German national standard, Deutsche Institut für Normen. Right? But in fact, all these testing, like tensile testing machine or tensile testing of material, you have corresponding tests, like basically the same test under different standards. For example, if you're using ASTM standard for tensile testing, you would use ASTM E8, right, for standard test methods for tension testing of metallic materials, right? But there's a corresponding Japanese standards, JIS 2241, which is corresponding to ISO 6892-1, right? Which is method of tensile tests for metallic material. And it will be quite similar. The testing method will be quite similar between the ASTM methods and JIS method. Bear in mind, the ASTM standard usually have the imperial version and also the metric version. So if you're choosing the metric version of the ASTM standard, it will be really, really similar to the JIS standard or the ISO standard. Okay. For impact testing, again, you have like JIS standard or ASTM standard, which is like basically the same standard that they apply in different countries. Okay. So these are the list of standard of the testing method that we have covered so far today. Right. So tensile testing, impact testing, hardness testing, and fatigue testing. Right. Different standards for these like testing methods. Okay, so the second part of this class is the failure of metallic materials, right? So we've learned about mechanical properties of metallic materials. Next, we will look at the mechanical failure of metallic materials, right? So first of all, we have to know about failure analysis, okay? And you can use this technique of the step to find failure in any field of study, right? So first of all, we have to define what is engineering failure, right? Engineering failure are events where a human-made structure or system fail to perform as intended, resulting in damage, injury, or death. Right. So this is a famous case. This is the Tacoma Narrows Bridge, right? A bridge in Tacoma, Washington, USA, right? It is a suspension bridge, and this is the bridge that linked the Tacoma Narrows in this area, the wind is really, really strong. Right? When they designed the bridge, they didn't account for the wind loading. And you can search on YouTube for Tacoma Narrow Bridge incident. You can see that the bridge is sort of twisted, right? In this picture here, you can see the bridge is twisted because the wind is really strong and making the bridge sway so much that the bridge twisted and eventually the bridge breaks apart, right? Because of the wind, right? So this is a failure by the engineers to account for the wind load, to account for the strong wind in that area, right? In this picture here, this is the space shuttle Challenger. Okay, the space shuttle Challenger exploded while it was being launched live, right? It was broadcast live all over the world, and all 7 astronauts passed away during the launch, right? So the space shuttle took off, and after 73 seconds, it exploded. And it was important event in that year because one of the astronauts was a kindergarten teacher, and she was trained as an astronaut to go up and do some experiment and like to communicate with like children, etc. And she was quite popular before the launch as well. But because of the miscalculation during the launch, the space shuttle exploded and all these astronauts died. What was the miscalculation? Basically, space shuttle was launched in Florida, right? In Cape Canaveral. And usually, Cape Canaveral is quite warm. And in this case, it was launched on January 28th, 1986, and it was unusually cold. In fact, it snowed a couple of days before the launch. In fact, it was scheduled to be launched on the 26th, but it was too cold, it snowed, and the temperature was too low. They postponed it until the 28th. The sky was blue, but the temperature was still cold. There was no snow anymore, but the temperature was cold, right? They started to go ahead with the launch, but because of the cold weather, that made the launch disastrous, right? Because on the rocket of the space shuttle, you need O-ring, right? So basically a piece of rubber O-ring that seals the oxygen, the liquid oxygen in the tank. But because of the cold temperature, the O-ring fails to expand and seal the liquid oxygen properly, and there was a leak of liquid oxygen, and that makes the explosion occur, right? So basically, some materials, when you're using it at different temperature, the property will be different, right? So a lot of the rubber, a lot of the elastomer, when you're using it at low temperature, it's not elastic anymore. So you can try by putting a piece of rubber band in the freezer and try to pull it. It will feel really stiff. It's not like elasticy anymore. Right? So basically, these are like a failure, right? And we have to do failure analysis. The objective of failure analysis is to understand the causes of failure so that we can prevent future failure and improve materials and design. Okay, these are the steps that we use to do failure analysis. So basically, we do the preliminary examination, like looking at all the evidence. We do sample collection. We do microscopic examination. Right. So basically, using microscope to look at fracture surface, look for clues. We do like microscopic examination, chemical analysis, mechanical testing of the material, whether it has the same um, property or not, like factography and documentary. Right? Okay, if you remember during after the earthquake in Thailand last year, right? Um, um, One of the things that they try to do, like during failure analysis of the collapsed building of the uh, uh, an, an official government building, right? So one of the things that they do was take the um, reinforcing steel from the building and do mechanical testing to see that whether the reinforcing steel is strong enough according to the standard and according to the building practice for that type of building, right? So that is one of the step, right? Other step is to chemical analysis, microstructural analysis, etc. Right? So these are all failure analysis process. Okay, so there are different type of failure, right? We have thermal failure. So when you have excessive heating or temperature fluctuation, you have thermal failure. You have electrical failure when you have excessive electrical loading, right? And you have mechanical failure when you have uh, excess mechanical loading, like fracture, or when you are using it at high temperature for a long time, you would have creep, right? Or if you are using it, if you're applying cyclic stress, you would get fatigue, right? And then you would get chemical failure, which is corrosion, which we've covered in another lecture. Okay, so if we are applying a constant stress and our material cannot withstand that stress, what would happen, right? What would happen is fracture. Okay, so there are two types of fracture. Right, so okay, sorry. Let's go back a little bit. So, what is fracture? Simple fracture is the separation of a body into two or more pieces in response to an imposed static stress. Right. So I have to say that we are talking about static stress. Right. So a constant stress at a temperature that are lower than the material melting point, right? So what these two or three lines trying to say is that the stress is constant at low temperature, so we're not talking about fatigue or we're not talking about creep, right? We're talking about a constant stress at low temperature. So that stress makes the component breaks into different pieces, break into two or more pieces, right? And we can categorize materials based on their fracture behavior. We can have brittle material, right? Brittle material when we have small elongation, okay, and we can have ductile material when we have high percent elongation, right? Okay, percent elongation is basically percent strain, right? So basically, for brittle material, that means when you're applying tensile stress, it doesn't stretch too much, right? It breaks quite easily without getting stretched, without getting a lot of strain. Okay, so it is quite brittle. You have small amount of elongation, and the other type of materials are ductile material. When you have large percent elongation or large percent strain, it will be stretched quite a lot before it breaks. Okay, so for brittle material, you have brittle fracture, you have little or no plastic deformation. Okay, so the fracture surface is quite flat. There's no warning. It is a catastrophic failure. There's no warning. Okay, um, ductile fracture is usually accompanied by significant plastic deformation. There's warning before fracture. Okay, the warning that we're talking about in this case is the deformation, the plastic deformation or elongation of specimen, right? Ductile fracture is usually more desirable than brittle fracture because it gives us warning, right? So for brittle fracture, it doesn't give you any more warning. You are using it in 1 minute, and then the next minute it will break straight away, right? It doesn't give you any warning at all. But if your material is ductile and you're using it, after a certain period of time, you will notice a certain amount of plastic deformation, right? And we call that a warning, right? Because if your material is starting to deform, we can say that okay, maybe it's time that we replace it or repair that component before it breaks. Okay, so deformation can be a good thing. Deformation can be a warning that we can replace that component before it breaks. Okay, ductile fracture usually breaks into one large piece with large deformation. Like in this pipe here, you can see that the pipe is heavily deformed, but it breaks into this just one large piece. Whereas brittle fracture will break into many different pieces. Each pieces has small deformation. So if you can gather all the pieces together, you can just sort of like glue them back together, right? Because each of the pieces doesn't have a lot of deformation. The shape doesn't change a lot. They don't deform a lot. So when you glue them back together, they sort of retain the same original shape as before. Okay, so what happened during ductile fracture? So if you recall the impact testing, right? You can see that high toughness material has like a lot of dimples area, right? A lot of rough surface area compared to low toughness material or brittle material, right? Brittle material will have a lot of cleavage or flat fracture surface, right? If you recall that, you can see that for ductile material, you have a lot of dimples. So what does that tell you? It tells you that usually materials that are ductile are usually tough also, right? Because they have the same behavior, right? It gives you like a lot of dimples, okay? And what happens to give you that dimples? Okay, when you are applying tensile stress, initially you get uniform elongation until you get necking, right? And after you get necking, you start to get void nucleation. Okay, so you get void nucleation, you get like void around the impurities, right? So impurities particles. Like in this picture here, you can see a lot of impurity particles, and you start to get void around those particles. And if you keep pulling the specimen, the void will start to grow and link up, right? So you get void growth and linkage. So you can see that the void will get bigger. Okay, the void will get bigger and will link up in this void growth and linkage. And eventually, you can see that there's a big hole inside your specimen, right? And that big hole cannot withstand any load at all. So all the load, all the stress will go through the outside of the material, like this area here, right? So that will be that material won't be able to support the loading that is being applied. So there will be a shear overload. So you get this shearing at the surface. So eventually you would get a fracture with a typical cup and cone fracture surface, right? So you get a cup like from this piece here, and you get a cone from this piece, right? So you get a cup and cone fracture surface, which is typical of moderately ductile fracture. Okay, so if it is a tensile loading, you would get a more of a spherical dimples. But if you get a parabolic dimples, like in this picture here, right? So if you get a parabolic dimples, that usually means your specimen is experiencing shear loading. Okay, so this is moderately ductile fracture. For brittle fracture, you can divide brittle fracture into two types. You get transgranular brittle fracture and intergranular brittle fracture. You can see that for transgranular brittle fracture, the crack will go through the grains, right? So trans means across, granular is the adjective of grain. So transgranular means across the grain. So the crack will go across the grain, like in this picture here, you can see the dark crack go through the grain boundaries, right? This is transgranular fracture. You get flat, relatively flat fracture surface, right? For intergranular fracture, you can see the crack will go between the grains. Inter means between, right? So the crack will go between the grains, and you get this sort of fracture surface. You can see grains here, whereas like the grain are sort of like deformed a little bit, like in this cleavage structure. Okay, so this is the brittle fracture. Okay, so when you compare ideal material to real material, we find that the tensile strength of engineering material, like real material, is a lot less than perfect material, right? Perfect or ideal material at room temperature, the tensile strength of the real material is a lot less than perfect material. The reason for that are flaws or defects. Okay? Because flaws can cause premature failure. A larger sample contains larger flaws, and larger flaws and longer flaws and more flaws in general, right? So flaws are stress concentrators. There's a simple experiment that you could try. If you have a glass steering rod, and if you try to bend it, it might break quite easily. But if you take that same glass steering rod and you just dip it in hydrofluoric acid, for like 5 to 10 minutes. It will become stronger, not by any like magic or anything, but because hydrofluoric acid will etch the surface, it will eat away the surface, and it will eat away all the shallower cracks on the surface, making your glass steering rod cleaner with less flaws. So that makes it stronger. Okay. Usually, fracture is caused by crack propagation. So basically, you need a crack, right? You need a crack, and you need that crack to grow to get fracture, right? So we assume that most material have flaws. Okay, so to get fracture, the stress that is applied have to make the cracks grow. Okay, and cracks having sharp tips propagate easier than crack having blunt tips. Right, so for brittle material, we usually have sharper tip, and the stress concentration at the tip is really, really high because of the sharpness of the tip. Okay, so brittle material will break or fracture much more easily than ductile or tough material, because a ductile material can blunt the crack tip by plastic deformation at the crack tip. Right, so you get plastic deformation at the crack tip and blunt that crack tip and make the crack grow slower for ductile material. Right, crack blunting decreases sigma m or mean stress, and we have more plastic deformation at the crack tip. And ductile tearing consume a lot of energy by plastic flow, and this is why ductile material are tough. Right, so basically, what these paragraphs says is that ductile material consume energy by blunting the crack tip, by plastically deform the crack tip. They consume a lot of energy, making ductile material tough at the same time. Okay? Whereas brittle materials doesn't consume a lot of energy, and at the crack tip you have a lot of stress concentration, so the crack will grow a lot faster in brittle material. Okay. Okay. So what is the criteria for crack propagation? The crack will propagate if the crack tip stress, or sigma m, right, is higher than the critical stress for crack propagation, or sigma c. Right? So basically, when we apply stress, and because of the shape of the stress, we get the stress at the crack tip, right? For a ductile material, the sigma m will be decreased because of the plastic deformation, but for brittle material, the sigma m will increase because of the stress concentration of the crack tip. Right? If the sigma m or the crack tip stress is increased so much that it is higher than critical stress for crack propagation, or sigma c, where sigma c is equal to E gamma s over pi a to the power of a half. Right? So if sigma m is higher than sigma c, then the crack will grow. In other words, if the stress at the crack tip is higher than the critical stress for crack propagation, which is a material property, right? Because if you can see, Gamma S is the specific surface energy, which is a material property. E is the modulus of elasticity, which is a material property. And A is the length of the internal crack, right? Which is, we can fix this to be like a certain value. So you can see that if sigma m is higher than sigma c, then the crack will grow, right? For ductile material, we replace gamma S with gamma S plus gamma P because we have plastic deformation as well, which is uh, the energy that is consumed by plastic deformation at the crack tip. Right? So you have another term here. So the stress, or in other words, the sigma C for ductile material will be higher than sigma C for brittle material. That's why ductile material is tougher because it is more difficult for crack to grow, right? Because you have this term here, sigma y plus, gamma S plus gamma P, right? For ductile material, you have another term, an extra term here that makes sigma C higher for ductile material compared to brittle material. Okay, so this is the fracture toughness of different materials. You can see that a lot of materials are quite tough, like metals. Metals are quite tough, whereas um, polymers, ceramics are quite brittle. Although they have low fracture toughness, and composite material have like the best of both worlds. You have like high fracture toughness as well. Okay, what is the importance of fracture toughness? It is the material property that you need when you want to choose a material that can withstand a lot of not just impact but repeated impact and repeated apply energy without breaking. So, for example, if you choose a material for say for root canal, right? You can choose either metals, ceramics, or polymers. You can see that metals have higher fracture toughness. That means it can withstand like the repeated action of like chewing without breaking, right? But if the screw that is for the root canal is made from ceramics, it can crack quite easily because it has low impact and low fracture toughness. Okay, so from sigma c equal to E gamma c over pi a to the power of a half, we get sigma square root pi a, and we get square root E gamma c, right? So from this, right, we rearrange, we get that this is the stress intensity factor, this is material property, right, the gamma and E, right? So we make that equal. Okay, so what that means is that the largest crack, most highly crack will grow first, right? The stress intensity factor tells you that, right? So if you have higher A value, which is the length of the crack, it will grow first, right? Okay, fracture toughness is a material property that measure materials resistant to brittle fracture when cracks are present. This property can be defined by parameter Kc that relates the critical stress for crack propagation and geometry of the crack. For crack growth condition, K is more than or equal Kc, which is equal to y gamma c sigma c square root pi. Right. So scenario one, when we have a max floor size, and that can dictate the design stress, right? So sigma stress is less than Kc over y square root pi a max. Okay, so basically, when you plot a graph of stress and sigma and sigma max, you will get fracture if the value is above this line. Scenario 2, when the design stress dictates max floor size. Okay, so sigma max is less than 1 over pi Kc over y sigma design squared. Okay. Okay, fracture and geometry, load, and material. Right. So for crack growth condition, the stress intensity factor Kc must be higher or equal to K. I'm sorry. For crack growth condition, stress intensity factor K must be higher or equal to Kc, which is fracture toughness. And the stress intensity factor is the stress at the crack tip, which depends on the load and the geometry of the crack. Right, so Kc equals sigma square root pi a. When you have like internal crack like this, right? When the length of the internal crack is 2a, and K is equal to 1.1 sigma square root pi a. When you have external cracks on the surface, and the crack length is a. Right, so these are the two different values of stress intensity factor. And if this value of K is higher than Kc, which is material property like we've seen before, right? Kc is material property. Kc is material property, right? So if K is more than or equal to Kc, crack will start to grow and you start to get fracture. Right, so Kc is the fracture toughness of a material. Depends on the material, depends on temperature, environment, and rate of loading. When the sample thickness is much more than crack dimension, we get a plane strain condition where Kc is equal to K1c. Right, when 1 in this case refer to the crack opening mode. In this case, when you have K1c, when we have plane strain condition, the crack propagation is independent of thickness of the specimen. So we get K1c equal y sigma c square root pi a. This is the plane strain fracture toughness. Okay. Okay, fracture and impact testing. Well, if you recall the impact testing we discussed earlier, right? We have the impact testing machine, we have the specimen, we have the hammer, we hit the hammer, blah, 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 right? And we can divide material into 3 groups. The ductile or tough material, the green line here. We have brittle material, the blue line here, right? And material with ductile to brittle transition, the problematic material here, right? The magenta line here, right? So the BCC metals like iron at temperature lower than 914 degrees Celsius. Some polymers behave like this. This is very diplomatic because if you design it to be used at a temperature above DBTT or the ductile to brittle transition temperature, but it was used at a lower temperature, it will cause like cracking, right? Like the Liberty ship that I've explained earlier, that the crack happened in the middle of the ship, or even the Titanic, right? The Titanic was designed to be used at a temperature like above. Well, first of all, the Titanic was made from BCC metals like iron, right? Not good quality iron at that. And at that time, it was unusually cold, and you have iceberg coming down so far south. And when it hit the Titanic breaks because it is so cold that the Titanic behave in a brittle manner. Okay. Um, okay. So low temperature makes material more brittle, and it will decrease toughness. So that's why the Titanic breaks quite easily when it hits the iceberg. Okay, we call fatigue testing, right? So we do the rotating bending. Key parameters of fatigue is uh, mean stress, which is sigma max plus sigma mean divided by 2, and stress amplitude, which is sigma max minus sigma mean divided by 2, right? So mean stress here, stress amplitude here. So fatigue can cause failure even though sigma max is less than yield strength of material, responsible for about 80 to 90% of mechanical failure. Okay, we can divide material into two types: the one with fatigue limits and one without fatigue limits. Right. So from earlier, if you recall, right. So the 1045 steel has a fatigue limit, right? Whereas 2014 T6 aluminum doesn't have a fatigue limit. Okay, what does that mean? Okay, a material with a fatigue limit is a material that you won't get any fatigue if the stress amplitude is less than fatigue limit. Say, for example, if you're using it at this stress amplitude, like at this point here, right? So you won't get any uh, fatigue. So it will stay safe if you're using it at a stress amplitude below S fatigue, right? This is the case for steel, right? For some other materials like aluminum alloy, you don't have any fatigue limit, so you have to be careful how long you will use it, because at a certain stress amplitude, you can only use it for a certain amount of time before it fatigue. Okay, and you can improve fatigue life, by imposing compressive stress on the surface, like shot peening or carburizing, right? So basically, if you increase the compressive stress on the surface, you will shift the graph, right? The SN curve from this one here, the one on the bottom one, to the middle one, to the top one. And you can see that if you're using it at the same stress amplitude, right, the same stress amplitude here, you can see that the number of cycles to failure will increase, right? So for a larger sigma m, you get this SN curve here. For a moderate sigma m, you get this SN curve. For a near zero or compressive sigma m, you get this SN curve, right? So for a larger tensile sigma m, that means you have positive sigma m, right? And how do you change from larger to moderate to zero sigma m? So basically, you apply a negative stress. What is negative stress? Negative stress is compressive stress. Okay, so from a larger sigma m, when you apply negative stress, that larger sigma m will transform into moderate sigma m. So the SN curve will shift from this line to this line. If you increase even more compressive stress, the SN curve will shift further to this line. Okay, so you can see that the number of cycles to failure will increase from this much to this much for the second line and to this much for the third line. So in other words, fatigue life will increase as you increase the negative stress on the surface. And you can do that. You can increase the negative stress on the surface by doing shot cleaning, just like sand blasting, but instead of using grains of sand, we are using stainless steel shots, like shooting stainless steel shots on the surface, making the surface compressive, shifting the SN curve. Or you can do carburizing process. So instead of like shooting it with stainless steel shots, you are introducing carbon atoms on the surface, right? So you're putting your specimen in a furnace, and in that furnace it is carbon rich. You have carbon monoxide and you have methane gas. Right? Where you have carbon dioxide, carbon monoxide, methane gas. You heat it up, and the carbon will stick to the surface, and the carbon atom will move inside the surface, making the surface of the specimen more crowded. So you have more compressive stress, and that will make the fatigue life better. Another way to make fatigue life better is by better design. When you remove stress concentrators, like this sharp angle here, if you fillet the angle, you will get a rounded angle. This is a better design. You get better fatigue performance. Okay, creep. Okay, recall creep testing on page 39. Okay, so when you apply a constant stress, right? So this is a graph of time and stress and strain, right? So if you apply a constant stress, you should get a constant strain. That is usually the case if the temperature is less than 0.4 Tm. But if the temperature is more than 0.4 Tm or 40% of the melting point, you start to get creep curve, just like this, right? When the x-axis is time and the y-axis it is creep or strain, and the slope is the creep rate. The primary creep, right? The slope of the primary creep or the creep rate decreases with time. For the secondary creep, you have a steady state creep, which is the constant creep rate, and tertiary creep, you have like increasing slope really quickly, and because of the necking, right? And you get like fracture strength. Okay, and you can see that you get failure along the grain boundaries. You get holes and grain boundaries cavities because of the movement of the atoms. And at grain boundaries, the atoms can move quicker, so you get a lot of holes along the grain boundaries at high temperature. And as you increase temperature and as you increase the applied stress, you can see that the creep curve will shift from the green line to the blue line to the red line. So basically, the creep will occur faster and you will reach failure faster also. And mechanical failure summary. So engineering material engineering material is not as strong as predicted by theory because of flaws. Flaws act as stress concentrators that cause failure at stress lower than theoretical value. Sharp corners produce large stress concentrations and premature failure. Failure type depending on temperature and stress. For simple fracture, non-cyclic, like constant stress, and temperature of less than 0.4 Tm, failure stress decreases with increased maximum flow size, decreased temperature, and increased rate of loading. Right? Failure stress means the stress that you have to apply to break a piece of specimen. Right? You require less stress if you have maximum flow size. You require less stress if you decrease temperature. Okay, if you decrease temperature, material are usually more brittle, right? If you increase the rate of loading instead of like constant loading, you change it to impact loading, the material will become more brittle as well. For fatigue, so cyclic stress, fluctuating or dynamic stress, cycles to failure decreases as stress amplitude increases. Right? For creep, constant stress at temperature above 0.4 Tm. Time to rupture decreases as you increase the stress or increase the temperature.